The Open Systems Interconnection, OSI model, conceived by the International Organization for Standardization, ISO, is a reference model that serves as a foundation for harmonizing standards development to facilitate systems interconnection. The Internet Protocol Suite, established concurrently with the OSI model, was predominantly backed by the U.S. Department of Defense and served as a pivotal framework for the inception of the Internet, concentrating primarily on the software layers of communication, employing a structure akin to, yet less stringent than, the OSI model. While various models have attempted to elucidate networking concepts and processes, the OSI reference model has emerged as a paramount standard for discussing and educating networking within the realm of information technology, allowing seamless communication through the exchange of protocol data units, PDUs, between involved parties, a concept known as peer-to-peer networking. Unlike the Internet Protocol Suite, which adopted a less prescriptive approach and was spearheaded by the Internet Engineering Task Force, the OSI model encountered challenges in achieving widespread adoption due to the emergence of multiple proprietary networking standards. Despite the ongoing debate in the late 1980s and early 1990s regarding the superiority of the OSI model versus the Internet Protocol Suite, TCP/IP eventually gained prominence for Internet working, overshadowing the original protocols envisioned within the OSI framework. Presently, while the OSI model continues to serve as a cornerstone for educational and referential purposes in networking, some experts argue its pertinence to modern cloud computing, while others advocate for a more streamlined approach that aligns better with contemporary networking protocols. The physical layer of a network handles the transmission of raw data through various mediums by converting digital bits into electrical, radio, or optical signals. Specifications include voltage levels, data rates, modulation schemes, and connectors. Common issues at this layer can arise from media termination errors, noise interference, and misconfigured network devices like NICs and hubs. Standards like Bluetooth, Ethernet, and USB rely on physical layer specifications, with lesser-known examples like the CAN standard also falling under this category. The data link layer facilitates node-to-node data transfer between directly connected nodes, detecting and potentially correcting errors from the physical layer. It establishes protocols for connection, flow control, and error checking. Sublayers include the MAC layer, regulating device access to the medium, and the LLC layer, responsible for network protocol identification and error control. Networks like Ethernet, Wi-Fi, and Zigbee operate at this layer, with protocols like PPP functioning over various physical layers. The network layer manages packet transfer between nodes in different networks, utilizing addresses for message delivery and possibly routing through intermediary nodes. This layer may split messages into fragments for transmission and does not guarantee delivery reliability. Functions like routing protocols and address assignment fall under network layer management, and security like IPsec can be implemented here. The transport layer enables variable-length data sequences to move between hosts while maintaining quality of service functions. Protocols may be connection-oriented or connectionless, with the layer responsible for segmenting data into manageable chunks and providing reliability through flow control, error correction, and acknowledgement. Protocols like TCP ensure successful data transmission, retransmitting segments if necessary. The session layer establishes, manages, and terminates sessions between computers, handling functions like user logon and log-off, authentication methods, and data stream operations. This layer supports full duplex, half duplex, or simplex operation and manages connections between local and remote applications. The presentation layer formats and translates data according to the application layer's requirements during both message encapsulation and dencapsulation. It handles data encryption, compression, and decompression, ensuring compatibility between different systems and graphic commands. The application layer, closest to the end user, interacts directly with software applications like web browsers and email programs for communication. Functions include file sharing, message handling, and database access via common protocols such as HTTP, FTP, and SMTP. It identifies communication partners, distinguishes between application entities, and does not determine network resource availability. Cross-layer functions are essential services that transcend individual network layers, impacting multiple layers simultaneously. Aspects like management and security have broad implications across all layers, aiming to enhance data confidentiality, integrity, and availability. The interaction between network design and management protocols significantly influences the availability of communication services, making cross-layer functions pervasive in practical implementations. For instance, management functions encompass configuring, monitoring, and terminating communications among entities, requiring interaction with all layers using protocols like Common Management Information Protocol, CMIP, and its service counterpart, CMIS. Multi-protocol label switching, MPLS, ATM, and X.25 stand out as examples of such cross-layer functions. Moreover, the OSI model further categorizes the network layer into 3 sublayers: subnetwork access, subnetwork dependent convergence, and subnetwork independent convergence. These subdivisions aim to provide a unified data carrying service for both circuit-based and packet switching clients, accommodating diverse types of traffic, such as IP packets, ATM, SONET, and Ethernet frames. Additionally, in wireless network environments, cross-MAC and PHY scheduling plays a crucial role due to the dynamic nature of wireless channels. This scheduling optimizes network throughput by transmitting packets only in favorable channel conditions, requiring the MAC layer to acquire channel state information from the PHY layer to enhance efficiency and prevent energy wastage. In the realm of program interfaces, the OSI reference model and its protocols do not define specific programming interfaces, apart from offering abstract service descriptions. Software interfaces like the Network Driver Interface Specification, NDIS, and Open Data Link Interface, ODI, bridge the gap between the media and network protocol layers, facilitating seamless communication. Furthermore, a comparison of OSI layers with TCP/IP protocols reveals a rough correspondence, highlighting the distinctions between the 2 networking models, with each system having its unique characteristics and nuances.